All right. Well, thank you everyone for joining for another webinar for this month. Before I introduce our speaker, we will not have any webinars for the next 2 months, and we will resume on August. Our August webinar is an in-person meeting during the Image conference, so I look forward to seeing you all in there. Unfortunately, I won't be there, but most of our members of the subcommittee will be there, including Laurie and the chair and of the NSTS committee and so many other people. So I'm really sad that I'm not going to be there, but I look forward to hearing about that. And where the next webinar will be starting on September. We'll let you know who's going to be the speaker, and we'll continue this as we move into future. And hopefully we're going to have a workshop sometime early next year. We still are trying to finalize the details and how to do it, but this workshop will revolve around uncertainties in hydrology and hydrogeophysics, particularly groundwater exploration and estimating all the parameters comes with hydrogeophysics during the surveys. Once we get that finalized, I will update everyone on Slack, and we will have some, just like the webinars, ads on social media and everything, and I look forward to seeing you during that workshop as well. Today, we're really happy to have Teddy Herring. Teddy is a postdoctoral associate at the University of Calgary in the Department of Civil Engineering. She received her PhD in geophysics from University of Calgary and completed her first postdoctoral project at the University of Ottawa on permafrost geophysics. So, believe it or not, permafrost is also hydrogeophysics. So, frozen water is also counted as water. Her research interest centers around using geophysics to characterize and monitoring permafrost conditions for environmental and engineering applications. And thanks, Teddy, for being here for us today. And without further ado, I give the to you to start speaking. Thank you.
Awesome. Well, thanks for having me. That's it's really nice to be here. All right, everything look good with the PowerPoint screen? Yay, sweet. Okay, yeah, let's just get into it. I'm hoping this will be a short and sweet presentation, maybe somewhere around the 40-minute mark, so we'll have lots of time for discussion and questions afterwards. So thanks everyone for coming. I will be talking about geophysical monitoring of permafrost today. So you already heard the nice introduction, but I do like to just provide a little bit of background. My PhD was in geophysics at the University of Calgary. And in that project, I was looking at sites in northern Canada that had high potential for groundwater contamination and how we could monitor those using geophysics. And because there was a seasonally frozen surface layer that was actually really interfering with the signal of interest that I was trying to measure, I ended up reading a lot of papers on permafrost geophysics. And that led me to my first postdoc at the University of Ottawa. And I worked with NSERC PermafrostNet, and I was at the Department of Geography there. And I really got into the world of permafrost geophysics. And the key deliverable from this postdoc project that I did was I created a database of ERT surveys of permafrost and also published some guidelines for people who were interested in doing ERT surveys, but maybe weren't geophysicists and didn't have all the background information to know how to best acquire and process and interpret the data. And then I moved on to my current position, which is as a postdoc in the Department of Civil Engineering back at the University of Calgary. And in this project, I'm looking at the Hudson Bay Railway, which is a railroad in northern Manitoba, Canada. And they've experienced tons of problems since it being built in, I think, the 1920s, just due to permafrost thaw and settlement. And it's really been a problem for the railroad. So in this project, I used geophysics and a little bit of remote sensing to characterize permafrost conditions. And that kind of feeds into, thermal modeling and risk assessment, and hopefully some testing some mitigation strategies. So first, I'm going to talk about permafrost, thaw, and impacts. I know y'all are experts on hydrogeophysics and ERT, but I realize that not everybody has a background in permafrost. So I'll just do my like brief permafrost 101 to get everybody on the same page. So permafrost is just defined as earth materials whose temperature remains at or below 0 degrees for 2 or more consecutive years. And I like to show this image because most of the time we can't see permafrost, it's underground. But in this case, researchers have excavated a permafrost mound in the summer. And you can actually see in the lower portion of this, we have some darker material, and that's the permafrost. And you can see some reflective, shiny bits, and that's actually the ice in the permafrost. And above that, we have the layer that freezes and thaws seasonally, and we call that the active layer. And we find permafrost basically anywhere that it is cold enough. So lots of permafrost in Canada and Alaska and in Russia. So high latitudes where things are cold, we see permafrost. And we also see it at high elevations where it's cold. So the European Alps, the Tibetan Plateau. And in some areas where it's unglaciated in Antarctica, we can also observe permafrost. So we all know that the climate is warming, but I like to show this time series just to show the spatial heterogeneity of warming. So this is the surface temperature anomaly. This was put out by NASA. This is the most recent one I could find. And this is showing the surface temperature anomaly relative to 1951 to 1980 average. So of course it's, you know, pretty variable, but somewhere around the 1990s or so, we start to see this pretty pronounced warming trend. And that warming is especially strong in the Arctic. So you can see here that the warming in the Arctic far exceeds other spots in the world. And depending on who you ask, it might be about 3 to 4 times, warming 3 to 4 times faster than the global average. So as you can imagine, this really significant warming trend in the Arctic has pretty important implications for the state of permafrost and permafrost environments. So one of the impacts that we see of thawing permafrost in the north is damage to infrastructure. So these are all photos that I took in various places in the north, showing the impacts of thawing permafrost. On the left, we have, these are old buildings, to be fair. These were built during the gold rush in Dawson City, Yukon. So of course, our building standards are better today. We have more technology, but this is what happens if you build things on permafrost and don't really implement any mitigation strategies. So these are called the kissing houses. Obviously, nobody lives in them. They're just more of a tourist attraction that people can take pictures of. But you can see there's been a huge amount of settlement underneath these homes. And even though we have better building standards today, there's still lots of impacts of permafrost thaw, settlement, foundation cracking, and things like that in homes. Roads also, permafrost thaw is a huge hazard for infrastructure like roads. This one is not used or maintained, so it looks particularly terrible. This was a photo I took in Yellowknife, Northwest Territories, Canada. So nobody uses this road, it's not maintained, but if you were to leave alone a road built on ice-rich permafrost, this is something that you might end up seeing. So obviously big problems for infrastructure. This is a railroad, and you can see that there's quite a bit of track deformation happening related to permafrost thaw and settlement. So as you can imagine, a train cannot drive very quickly over track that looks like this. So there's all sorts of engineering and infrastructure concerns related to permafrost thaw. We also see some pretty dramatic landscape changes happening. On the left, I'm showing a drone image of a permafrost thaw feature called a retrogressive thaw slump. There's actually 2 here. And these are just when ice-rich permafrost thaws, you can get mass movements, and it exposes more ice-rich permafrost in the head wall, and it's this sort of gradually growing feature that eats away into the landscape until it stabilizes. And this one's kind of interesting because, as you can see in the background, there's a road. This is the Alaska Highway. This is the main highway through the Yukon. And you can see that they're actually diverting the highway in this image. So they had to move the road to accommodate this permafrost thaw feature. There's also concerns about all the sediment that's being dumped into the river. So what impacts does this have on aquatic chemistry and ecosystems? So lots of concerns. And this is just one type of permafrost related mass movement that we see. There's also changes in hydrology. We get thaw lakes or thermokarst lakes forming. There's also changes in groundwater surface water interaction. There's concerns about contaminant mobilization. There's all sorts of water related things that happen when permafrost thaws as well. And last thing I want to talk about is greenhouse gas emissions. So by our estimates, there's about twice as much carbon stored in permafrost as there is currently in the atmosphere. So this is in the form of organic material that's frozen in the permafrost. And when the permafrost thaws, this material becomes available for microbial decomposition. And that produces carbon dioxide or methane, depending on whether the environment's aerobic or anaerobic. And I show this video. This is some researchers at the University of Alaska Fairbanks looking at methane emissions from Arctic lakes. And this is fun to look at. It's very flashy and exciting, but it's quite a serious issue because the greenhouse gas emissions from thawing permafrost have the potential to significantly alter global warming trajectories, and it's not accounted for in the vast majority of global climate models. So there's this potential for a positive feedback loop of permafrost thaw, greenhouse gas emissions, warmer climate, more thaw, and concerns about positive feedback loops and tipping points and the impact that might play. So really the take home from this is that permafrost thaw affects northerners, but it's also a concern for everybody else in the world. Okay, so now that we've done the permafrost 101 stuff and hopefully convinced you why you should care about monitoring permafrost, here's a couple ways that we can measure it. And I'll start with some traditional monitoring modalities, and then I'll get into the geophysics, the stuff that everybody's most interested in. So one way we can measure permafrost is by frost probing. This is just pushing a metal probe into the ground to see how deep the active layer or thaw layer is. It's fast and easy, scalable and repeatable. It's minimally invasive. The drawbacks of this are that it's not possible in some terrain. So if it's rocky, or even if the soil is really clay rich, it can be hard to get accurate measurements. And of course, it requires us to go to the site and actually do these measurements. There is a global monitoring network that keeps track of all these active layer depth measurements, and that's called the Circumpolar Active Layer Monitoring Program. So the nice part about this is that there's a standardized methodology for collecting these measurements and a global monitoring network to kind of house these data and keep track of things at a large scale. Of course, we also use borehole sensors to measure subsurface temperature. This is great because it's a direct measurement of temperature. We can have high temporal sampling and see how things are changing throughout time. However, it is expensive and invasive. It can be hard to drill in some locations, and it is a point measurement. So we get lots of information at a specific location, but we don't have much idea of the heterogeneity of conditions across a site. So of course, this is where geophysics comes in and can really complement these types of data. For borehole sensors, we do have, again, a global monitoring network. The Global Terrestrial Network for Permafrost, or GTNP, is a network that houses all these different data points of borehole temperatures, so we can kind of get an idea of what's going on at a global scale. And now to the fun part, the geophysics. So I primarily work with electrical resistivity tomography, and this is a really common geophysical technique for monitoring permafrost. It's great because we're we're imaging subsurface resistivity. And that tells us a lot about permafrost because material tends to be much more resistive when it's frozen than when it's unfrozen. And you also see increases in resistivity at colder sub-zero temperatures. And it's just related to the amount of unfrozen water content in the ground. So with ERT, we can get 2D information, which is kind of your typical survey, like the one we're doing in this image here. We can do 3D surveys, and when we repeat them, we can get time-lapse information. They're minimally invasive, so we're not disturbing natural conditions. And ERT surveys can tell us things about temperature and ice content, water content, which are all things that permafrost scientists are interested in. The drawbacks are that it's an indirect measurement, so we're getting an estimate of resistivity, but we kind of have to interpret it in terms of what we actually care about, whether that's temperature or water content or whatever. And as with every geophysical method, there's some uncertainty associated with it. Even though this method is super useful and being increasingly used to measure permafrost, there's no established monitoring network for these type of measurements. So just to bring your attention to the utility of this method, we published a review paper in 2023, and that was looking at a review of more than 300 literature publications where ERT had been used for permafrost. And I also used the collective knowledge of my co-authors to draft some best practices about how people can go about collecting and processing and interpreting their data. This is one of the figures from the paper, just showing the number of publications over time. And you can see that, over the last 20 years or so, the number of publications has grown by about an order of magnitude. So it's increasingly being used, and basically everywhere in the world that there's permafrost, this method is being used to study it. Now to the really interesting stuff, which is some of the recent advances in the field that I've been involved in. So I'll get to talk about some of the sort of cutting edge geophysical monitoring advances. So one of them is ERT permafrost monitoring in Canada. Second one is the development of automated ERT instrumentation. And the last one that I'll talk about is the initiation of some permafrost ERT databases. Okay, so first off, ERT permafrost monitoring in Canada. So this was not my project. This was led by my previous postdoc supervisor, Tony Levkovich at the University of Ottawa. I was fortunate to be involved pretty heavily in the data processing side of things and also in the field work, visiting all these monitoring sites in 2021. But it's certainly Tony's project, and I was just fortunate to work on it a little bit. But he gave me permission to share some of the results, so we'll get to look at some of those. Lots of different funding sources, and also lots of graduate students and field assistants that helped with data collection throughout the years. Okay, so these sites are located in northern Canada. These are all along the Alaska Highway, and they're located in Yukon and in northern British Columbia here. The sites all have a pretty similar feel to them, vegetated primarily by black spruce trees, and there's an organic layer and moss at most of these sites. They look pretty similar from what you can see in these pictures. And just looking at the timing of data collection, so different sites have different sampling rates when people were able to visit them and collect data. The earliest measurements were from 2008. And then you can see in 2021, when I helped Tony with his data collection, we got to visit all of these sites and collect a data point in 2021. So there's a pretty wide span, temporal span of measurement dates here. Okay, let's look at some results. So looking at sort of the more northwestern side of things, here's one survey. And what I'm showing here is the first survey, which was done in this case in 2012, and then the most recent one, which was done in 2021. So us permafrost people like to flip our color bars and show the high resistivity stuff in blue. So just to orient you there. And I would interpret this high resistivity material in the near surface to be permafrost. That's corroborated with borehole temperatures at most of these sites and frost table depths as well. So you can see that comparing these two images over time, the resistivity magnitude has decreased in this permafrost zone. So that to me is indicating some degree of permafrost warming over time. And I'm just kind of cherry picking a few different results along this transect just to give you an idea for how things have changed over time. Here's moving a little bit towards the southeast, another site where there's a pretty distinct permafrost mound and permafrost body here. And again, same sort of story. The resistivity magnitude is decreasing, and also the extent of these bodies seems to be shrinking. Again, moving more inland, same sort of story. The first survey in this case was done in 2010, comparing it to the 2021 survey. And same sort of story. We have a decrease in magnitude of this permafrost body. And at our most southern site, there's been a complete disappearance of permafrost. Again, as corroborated by borehole temperatures and frost table depths. So at the southernmost limit of the permafrost zone, we're actually seeing that permafrost boundary shift northwards. And there's probably many locations along that southernmost boundary of permafrost extent where things have thawed completely. And one of the analyses that I did was looked at the average resistivity in that zone of interest in the red box that I drew on those images. So taking the average resistivity and looking at how that changes over time, you can see that there is a resistivity decrease at every site pretty consistently. So to me, that's telling the story of permafrost warming at all of these sites. You probably, I'm going to predict that somebody might ask a question about the site. This is milepost 681 along the highway. There's a very pronounced decrease in resistivity over time. And this site was a bit different than the others because there was some flooding that happened. So the site became inundated with water, and we expect that that really accelerated the thaw of permafrost at this site. So that's why this one looks a little bit different and why it decreases by so much. So when I'm interpreting these results, I'm seeing that resistivity is lowering. We're assuming that means a decrease in, or sorry, an increase in unfrozen water content, and relating that to permafrost warming and thawing at some sites. Now, something really interesting, when we look at the change in temperature over time, this is a plot showing the temperature, sorry, at the depth of 0 annual amplitude. This is a pretty common metric in permafrost science where we are taking the temperature at a depth where it's stable and not experiencing seasonal fluctuations. So looking at these stable temperatures over time, we can see that things are warming, but not really by a lot. So we know that air temperatures are warming. We know that the climate is warming at these sites, but the ground temperatures are changing very slightly, 0.2 of a degree or less. And you can also see that all of these temperatures, all of these sites are in pretty warm permafrost. So, somewhere in the like minus 1.2 to 0 degrees Celsius range. So it's very warm permafrost. So the idea here is that the air temperatures are increasing. There's more heat energy going into the ground at these sites, but that energy is going into the phase transition of ice to water rather than actual heating of the ground. So if we were just measuring these sites using borehole temperatures alone, we might not really get the full picture because it doesn't look like things are changing that much. But when we look at the electrical properties and we see pretty dramatic decreases in resistivity, we can understand that, hey, there's changes happening here, and it's mostly in the phase transition from ice to water. So the take-home messages here are that, well, first of all, repeated ERT surveys are a really great tool for identifying changes in permafrost. And second, that this is particularly useful for warm permafrost, where temperature might not be changing that much, but the resistivity changes are very large. Okay, now let's talk about automated ERT. Again, I'm just sort of a collaborator in a much larger project. So I have to give due credit to all the people that have worked on this project. This one was focused on developing low cost and robust automated instrumentation for monitoring permafrost. My role has been, I've dealt with a lot of the data processing side of things, and I was also fortunate to go to the Yukon last summer and help install the automated ERT system there. That's a picture of us after we got everything working. Everybody was very happy, despite the fact that it was raining and kind of miserable out. So a big team of international collaborators, lots of European folks that worked very hard on this, and it was funded by the Swiss Polar Institute. So here's how we set up the survey in the Yukon. We use these plate type electrodes to maximize the surface area that would be in contact with the ground. We buried all the cables just in the PD layer at the surface because there's lots of critters and squirrels and mice that might want to chew on our cables. So we buried everything so it was protected. And then the instrument itself lives in this weatherproof box. So the idea here is that we're permanently installing this equipment. And you can see here, well, it's not very clear in the photo, that's why I circled it, but there's a data transmitter that sends the data via satellite and a solar panel that keeps things running throughout the year. So this gets permanently put in place, and this system we set to collect data once a day and transmit it to us via satellite. So it's really exciting because a lot of like the monitoring that we saw in the previous example that required site visits once a year, hopefully, if you make it out there. But in this case, we could leave it running over time and just have it collecting data on its own, which is huge. One of the challenges, though, with data like this is there's just so much of it. So if you're collecting data every day, or for some other projects that I was working on with this, 3 times a day, you get these really large data sets, and we had to figure out how to process it in an efficient way. So, I mean, a lot of times with people, what people do is they'll collect their data and they'll manually remove data points, or somebody will be looking at it to identify poor quality data points and invert the data. But I wrote a Python code to automatically remove poor quality data points and using like consistent quantitative thresholds, and then perform a time-lapse inversion. This is just an example. Somewhere around, I think, mid-November, one of the electrodes must have lost contact. So you can see that in our raw data on the top figure here, that there's obviously a problem with one of the electrodes. And then the automated data processing routine is automatically filtering out those poor quality data points associated with that electrode. I made a GIF of the results. So this is showing starting in September of 2003 and looking at the resistivity changes in the subsurface over time. We can see the seasonal freezing from the top down happening in this case. That's that blue layer at the top. And it's really cool to get these temporally dense data sets so we can see what's happening on like a daily basis. So I inverted this up until some early May data. So there's more now that hasn't been included, but it is really cool to see changes over time. I guess I should note on the left side of the profile, there's no permafrost. And we know this is a site that's been previously instrumented. And the left side of the profile is this like wet, marshy stuff, and there's no permafrost under here. But this blue region, the high resistivity stuff, is permafrost. And I think what's happening at this site is that we're seeing some permafrost degradation, as evidenced by data that's been collected previously. The thaw layer has been getting deeper over time. And this red zone here, I would interpret this to be super permafrost talc or unfrozen region. So we think what's happening at this site is that the permafrost is actually thawing from the top down, and this part never freezes, even in the winter. So we are seeing some evidence of permafrost degradation at this site. And so project members for this AERT project have installed this equipment at various sites around the world. There's instruments in Antarctica, in Canada, that's the one I was just showing, in Kyrgyzstan, and in Switzerland. So the idea here is that by testing this equipment in these harsh and remote and extreme permafrost environments, fine-tuning things and making sure the instruments work as they're meant to, it's demonstrating the efficacy of these instrumentation and also establishing the basis for a global monitoring network using these time-lapse ERT surveys. So this stuff is super exciting to me. So the take-home message is here. We get these temporally dense data sets with automated ERT, and that's without the need for site visits. So you can imagine in places like Antarctica, for example, where it is super expensive to go visit, if we can place these systems and have them collect data over time without the need for site visits, that just opens up a whole new realm of possibilities for permafrost monitoring. And we can use this to detect long-term changes when we leave the instruments for a long period of time, and also short-term changes in permafrost. So we can start to look at things like how do precipitation events affect the subsurface? What does seasonal freeze up and thaw look like? So it's really neat to see these short-term events as well as the long-term events. And the last advance I want to talk about is permafrost ERT databases. So first I'll show you the Canadian Permafrost Electrical Resistivity Survey, or CPRS database. It's a bit of a mouthful. This was the main output for my last postdoctoral project. So I took more of a leadership role here. I was supervised by Tony Lefkovich. Funding came from NSERC PermafrostNet, and all these smiling faces you see here are just some of the people that collaborated on this project with me. The people you see here were data contributors, so they submitted data to the database, and then Nick and Etienne were really helpful in getting the database itself up and running. And I also have to thank some members of the International Permafrost Association Action Group that was looking at creating a global database of ERT surveys of permafrost. I was also involved in this group. These two projects were kind of running in parallel, so I'll talk a little bit more about this international one just after this. So the motivation for creating this database is that this is what the standard data storage system looks like for most researchers who are collecting these types of measurements. People go to the field, they go to all this effort to collect the data, and then it ends up living on people's field laptops and in field notebooks and on thumb drives. And maybe nobody even knows that this data exists except for the people who collected it. So the idea was to create a database that people could submit their data to and have standardized data and metadata, and really just make this data accessible for anybody who wanted to use it. Yeah, so the CPRS database, I created it and populated it with some data. This is a centralized location where people can submit their data. It has standardized metadata and data fields. The data is all processed in a consistent way, so we can start to compare different surveys to each other. And I also wrote the code for this interactive web map. I should have included, maybe I'll pop a link in the chat afterwards. But if you go to this website on the PermafrostNet website, you can search for different data. So if you want to access something that's collected within a specific time frame, or in a specific place, or of a specific landform, or what have you, you can filter through. And if you hover on any of these survey locations, this metadata will pop up to tell you a bit about it. And then if you click on it, it will show you the inverted survey results if they're publicly available. So with the intention of just making this very interactive, easy to search, and easy to access the data. So I can talk a little bit about what's in here so far. There are 209 profiles with 280 ERT surveys. So some of those profiles have time-lapse data, 15 of them to be precise. The data were collected between 2008 and 2022, and they represent 16 different landform types. So when people are submitting their data, I should note they're filling out a metadata form that describes in standardized language what the landform is, what the vegetation conditions are like, if there's an organic layer, what the disturbance is like, things like that for every ERT profile that's in the database. So one of the really neat things that I started doing with this is we have so much data, let's start making some broad scale interpretations of what's going on at like the continental scale. So one of the just first pass analyses that I did was plotting the average resistivity as a function of mean annual air temperature. And not surprisingly, we see that at colder locations, the resistivity tends to be higher. That makes sense because the permafrost is more continuous and deeper and colder. So it makes sense that we would see higher resistivities. But there's also a ton of scatter about this line. So I looked at the metadata to help explain some of this variability. So just showing some select results here. I can tie the resistivity variations to the landform type. So lithalsas and pulsas are both types of permafrost features where it's an ice-rich core. And so not surprisingly, we see that those types of features have higher resistivity, whereas features associated with thaw, like these thermal karst mounds, tend to show lower resistivity. So some of the scatter is attributable to landform type. Another really interesting thing that I noticed was there's quite a bit of variability that we can attribute to anthropogenic surface disturbance. So here I'm showing sites with no disturbance in blue, tend to have higher resistivities, and then sites with anthropogenic surface disturbance over 50% or more of the profile tend to have much lower resistivities. So these disturbance could be things like roads or pathways or airstrips or agricultural land, some kind of anthropogenic surface disturbance. So it's really interesting to see that there is potentially evidence of permafrost degradation as a function of human activities. And then to quickly mention the international database that I was just talking about previously, it was really fortunate for me because these two projects were kind of running in parallel. So we had a lot of collaboration and overlap between these two databases. This one was funded by the International Permafrost Association. And I mean, there was a ton of collaborators and data contributors on this, but the folks that were really leading the charge was the team at the University of Fribourg in Switzerland. So huge shout out to them for doing so much of the work, as well as all the other collaborators and data contributors. So again, I contributed the code for the website, so that's why they look so similar. But this international group has an international global database of ERT surveys. There's 403 profiles in it so far, data from 2002 to 2023. And part of the project also involved providing some support for the repetition of historical measurements. So that was in the form of a little bit of funding to support field work for people repeating these surveys that were older and then interpreting them in a climatic context. So someone applied for and received funding and was able to go out and repeat surveys that had been done 10, 12, 14 years ago. So this is a publication that was put together showing evidence of permafrost degradation in survey lines where they had repeated the same measurements 10 plus years later. So that's one of the advantages of these databases, is that by making this data available, we can start to repeat historical measurements and see how things have changed. And the take-home message here is that effective data management makes the data more useful for everyone. This was a photo. I love to include this. We were visiting Yukon before doing some field work this last summer, stopped at the Yukon Geological Survey, and someone was asking my supervisor, Tony, hey, I thought you did some surveys in, I think it was Mayo or Faro, somewhere in Yukon. I thought you did some surveys many years ago there. Like, what did you see? So we were able to pull up the website and just like right away, show the survey location, show the results. And it was really exciting to me. I snapped this picture in the background because it was just very exciting to me to see the databases being used in the way that I hoped they would. So really to conclude, I think that these three things that I talked about, these three advances, establishing monitoring sites, improving instrumentation, and working on developing effective data sharing practices, these are all factors that are going to contribute to the foundations for a global ERT permafrost monitoring network. So really exciting stuff. And with that, I'd like to thank everybody for joining and for listening. And I would be happy to chat, answer questions, or discuss anything you like.
Thank you very much, Teddy. That's was a huge work actually. I'm very impressed by the database management as well as the instrument. So it's open to questions. Everybody, please ask your questions in Q&A. I will also monitor the chat in case that the Q&A is not working. I'll start with the first question that is in the Q&A, which says, well, thanks from Sebastian. Thanks for presentation. Any recommendation for upscaling nonlinear degradation patterns over larger scales? I ask because of the likely patchy distribution of permafrost degradation at boundaries.
Oh, maybe I'm going to look in the Q&A so I can read the question. That was a long one. Okay, let's see. Recommendations for upscaling degradation patterns over larger scales. Yeah. Patchy distribution of permafrost at boundaries. Yeah, there's so many questions about how to effectively upscale these things. That's not an easily answerable question because, ultimately that's what we'd like to do for a lot of applications. Like, for example, if we're talking about global carbon fluxes, we would like to be able to upscale these site scale changes to continental or global scale changes. So that's one of the areas of research that I see being really exciting in the future is integrating site scale measurements with maybe things like remote sensing data or something like that. If we can tie these different types of change together. So that's one idea. Obviously, the more data that we have on the ground, the better. So I'd love to establish more monitoring sites in Canada and elsewhere so we can better fill in the data gaps between sites. Yeah, and yeah, permafrost degradation is certainly not homogeneous everywhere and is a function of, air temperatures and snow depths and all sorts of changes in vegetation, all sorts of other parameters that contribute to the variability of permafrost thaw. So getting a better grasp on those parameters would definitely help with the upscaling as well. Hopefully that answered your question, Sebastian.
So the next question is in the chat. So I don't know if you want to, I'll read it for everyone, but you can take a look at it. So this work from prior, sorry, I'm really bad with names. This work looks very interesting. I have just one query. It seems that you have done a time-lapse monitoring. So how have you taken care of the regularization parameter during the time-lapse ERD inversion? Is there any prior information that you included in these models or assigned weights to the time-lapse model?
Yeah, that's a really good question. So as you guys all probably know, there's lots of different styles of time-lapse inversion. The way that I did it, like for the Yukon data that I showed here, was to keep lambda constant and then do kind of a cascaded inversion approach where you were using the previous model as the starting model for each subsequent time step, so kind of a cascaded approach. And I'm sure that working more on this, there's probably more, there's different ways that we could approach the time-lapse inversion. So I'm definitely open to suggestions, but that's how we chose to do it for the particular data set that I showed.
Great. So I'll go over the questions in the Q&A again. The next question is from Roger asking, agreed that this is interesting and important. Have you transformed your resistivity versus time plots? I'm recalling your 6 or so sites along the profile you showed, including the one with the sharp drop that flooded, into actual free water content versus time.
Yeah, it's a little bit tricky to actually quantify the unfrozen water content. It's much easier to calculate the change in unfrozen water content relative to initial conditions. But unless you have something to constrain it, you can't really get like unfrozen water content. So looking at changes, yes, absolutely. And no, I haven't done that for that site yet, but that's a really good suggestion. And it would be pretty easy to do. Just has to do with the ratios and resistivity. And yeah, that would be a great idea. Thank you, Roger.
So the next question is from El Shalkani, asking, what is the depth or thickness range for these permafrosts?
Yeah, the ones at the sites that I was looking at here, these were all fairly warm sites. So if I'm just going to cheat and look at some of the inverted ERT images to see approximate depths, like the thicknesses are somewhere in the maybe, let's see. I should know this off the top of my head. Somewhere in the like, couple meters at the warmest sites to at the colder sites, maybe, 20 meters thickness or something like that. But of course, if we go farther north or to colder environments or places where there's been longer time for permafrost to degrade, then we can see much thicker permafrost. Like if we go way far north, it could be hundreds of meters thick. But the ones I was looking at here are on the warmer side of things and much thinner. Just to give you a ballpark there.
Just out of curiosity, my question is that below that is usually bedrock, or we may have actually unfrozen soil or something.
Yeah, my assumption would be that I actually don't know the depth of bedrock at most of these sites. The boreholes tend to be pretty shallow, but I would assume that at least at the shallow, the thin permafrost sites that we've got unfrozen soils underneath, and then probably deeper bedrock. But I actually don't know the bedrock depths for sure. That's a good question.
Another question from Randy: did you do any other geophysical surveys, GPR, TDM, FDM?
Not at these sites, but that would be cool.
I know a lot of people do a lot of GPR in those sites.
Yeah, definitely. I think at some of these sites that I showed anyway, it would be tricky because a lot of the soil is pretty clayey. So I am skeptical about whether GPR would work at these sites anyways, the Canadian sites that I showed. But yeah, absolutely. Like integrating multiple geophysical methods is really the strength here. So getting auxiliary information, whatever that looks like, is definitely an asset.
Next question is from Constantine, asking, you showed some ERT profiles with the maximum resistivity of 650 ohm meters. How are you sure that the soil is frozen? What is the threshold you define for frozen versus unfrozen?
Yeah, that's a good question. I mean, there's no one threshold that we can say that above this resistivity it's frozen and below this resistivity it's unfrozen. It's really site dependent, and it depends on things like the clay content of the soil and the moisture and the chemistry of the pore fluid and all these different things. But for example, when we see changes in resistivity, we can be pretty sure that that's attributable to changes in unfrozen water content, because we don't expect the geology to change. We don't expect the pore water to change. Really, if it's changing from 2010 to 2021, we can attribute that to a change in permafrost conditions. So it's not so much about the absolute value, but more about interpreting changes. And then, of course, if we have a borehole and if we have frost table depths and we encounter frozen ground with our frost probe and we see sub-zero temperatures in our borehole, that helps us to figure out that it is permafrost, even though sometimes the resistivity is not extremely high.
Right. Yeah.
Yeah.
Sounds true. The next question is actually answered, so that's great contribution from the community. So I'm gonna go to the other question. A great talk. I love the time-lapse images in particular. I'm wondering why some isolated high resistivity zones appear in the active layer. Would your data show information of ice wedges? Any other data support the results of the talic?
Okay, so I guess we're talking about the Yukon results, hey? Yeah, so there's isolated high resistivity zones in the active layer. There's definitely, the site is really interesting because there's lots of little mounds. So there's quite a lot of topographical variation. And a lot of these mounds, there's like little isolated chunks of permafrost. So that could be why we're seeing high resistivity zones in the active layer. I wouldn't expect to see ice wedges here. So typically I would expect to see ice wedges in areas where the permafrost is much colder, because we get ice wedges because it gets so cold that the ground contracts and cracks in the winter, right? So in these cases, I wouldn't expect to see any ice wedges, although I have done ERT surveys over ice wedges. Well, one or two. It's not something I have extensive experience with, but in the case where I was doing it, we were doing a really high resolution survey over an ice wedge trough, and we weren't really able to see much because the ground around it was also frozen and high resistivity. So it didn't produce as nice of results as I was hoping to see with an ice wedge. But some people have had success depending on site conditions, but so far I haven't really been able to see ice wedges.
Great. The next question is there from David asking, is there a way I can get the recording? So that was answered. The next question is that great presentation, Teddy. Do you know if there will be more drive to monitor permafrost and near surface geophysical changes as more carbon capture and underground storage projects are happening to help operators know if there is any potential of leakage?
Awesome. Hi, Anna. I haven't talked to Anna since we were in undergrad. We went to school together. That's so funny. Yeah, that's a really good question. I haven't really heard too much going on in the area of permafrost geophysics and carbon capture, but I'm sure somebody out there is doing it. But there's been a lot of research in kind of related fields related to containment. So I'm sure carbon capture would be much deeper stuff, but there's been work done, for example, with drilling sumps in Northwest Territories, for example. So again, same idea where the idea was to use to dispose of drilling waste fluid in permafrost and cap it in permafrost so that it's contained. So I wonder if there would be some overlap between that type of research and carbon capture, although carbon capture is much deeper, so it becomes a lot trickier.
Yeah.
Short answer is I'm not really sure.
There are new stuff they're doing it in the soil as well. I mean, I have a colleague who's is kind of trying to patent something about it. I don't know what they're doing, but that's it's just yeah. Anyway, the next question again from Roger asking perhaps a lighthearted question. Was there really an ERT permafrost result offshore equatorial West Africa?
That good spotting, Roger. Okay, so I wasn't actually the one putting together the all the data submissions for the international database. Somebody else was doing that. But I'm quite sure what happened there is a mix up between latitude and longitude because people put it in the wrong order. And there's actually several cases where they got flipped and they were plotting like in the middle of the ocean somewhere or in West Africa. So I think the odds of there being actual permafrost offshore equatorial West Africa is 0.
Or they chose the wrong datum when they used their GIS data and they just
Oh yeah, that could be it too. But
yeah,
yeah, my guess is a lat long switch because that has
Yeah.
popped up a couple times before. Good catch.
The next question is from Perry asking, you mentioned that you are involved in the HBR study group. Are you planning on using RT data for that work?
Sorry, RT data?
Maybe ERT data, I think.
Oh yeah, okay, that makes sense. Yeah, we actually got the opportunity to do some geophysical surveys last summer for that. So the project is still in its early years. It's, I think, a 7 or 8 year project that just started about a year ago. So we have done some field work already. The field work I was involved in was last summer, and we were doing some exploratory ERT surveys. So we did 11 ERT profiles at different sites in the northern portion of the railroad, and also some drone mapping, and some drilling as well. So ERT has been used in that region already, and my colleagues were just in the field not that long ago collecting a second round of field data that I haven't had a chance to look at yet. So yes, we have some data so far, and it's been really interesting to see the relationships between permafrost conditions shown in the ERT, and then also the vegetation and the peat layer and the surface water bodies and how those all influence permafrost. I didn't include any of it here, but maybe we can chat some other time about it.
Great. So the last question is from Ryan asking, "Hey Teddy, thanks for the great talk. Can we use these ERT time lapse as in conjunction with other geophysical survey to predict areas for potential thawing in the future?"
Oh yeah. So using changes that we see in the ERT images to make predictions about thaw. Yeah, that's a really interesting question. So one project that I worked on with a colleague was using ERT images and taking co-located resistivity values and temperature measurements from a borehole to translate ERT images into temperature models. So that's one way that we could use ERT, estimate temperature, and then use that as kind of a data point or a calibration point for a thermal model. So that was something that a colleague and I were doing at the University of Calgary, making some predictions about what permafrost might look like under the Hudson Bay Railroad in 50 or 100 years or whatever, using the ERT results as a data point there.
Great. Yeah, I'll look forward to that. Yeah.
Mhm.
Fantastic. So looks like there are not any more questions. So I'll ask one question out of oh, there's something in the chat.
I'm
Roger
impressed that
said,
there's so
"Smash
many
and
questions.
talk." All right. So yes, this is an ongoing project. I'm assuming these. So you said these instruments are low cost. What is the how much are they? The ERT
Ooh,
with the entire system that can transmit data and everything.
that's a really good question. So I remember earlier conversations. So I've been working really closely with Mohamed Farzamian, who's at the University of Lisbon, and he's really leading the charge on developing this instrumentation and kind of bringing it all together. And I don't want to get in trouble for saying the wrong number, but I will say that the automated ERT system, without the data transmission and the solar panel, was, I believe, less than half the cost of a ABEM parameter. So quite a bit cheaper. I don't actually know how much all the extra bits and bobs cost yet, which is something that I should actually probably have numbers for, but quite a bit less expensive. Although the drawback is that it's just some people making these instruments rather than a company who's kind of mass producing them. So you have to know the right people, and it might not be like one's off the shelf ready to go. So that's a drawback.
Yeah. Well, that's really exciting. Yeah. Thank you very much for having this talk. It was really interesting and really great work. I kind of looked at the database that you have there. A lot of good data, but a lot of data is under embargo.
Yep. Yeah.
But hopefully they're going to be released publicly soon. Well, thank you everyone for joining, and hope to see you soon at the Image Conference and in September. Thanks, Teddy.
Awesome. Thanks, everybody.
Goodbye.